Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the residue upgradation part. In the previous lecture, we have discussed on the removal of sulfur, nitrogen and metals from the liquid fuels. Now we will concentrate how the vacuum residue or the residual part can be upgraded to liquid fuels through different upgradation routes to make the product and the process more cleaner. So, the content of this topic, petroleum residue and its upgradation, then residue upgradation routes, the solvent deasphalting, visbreaking, delayed coking and gasification. So, these are different routes which are normally used. In this class, we will cover up to solvent deasphalting and the rest will be covered in the next part. So, now we know that when we process petroleum crude in the atmospheric distillation, it left some residue and then that atmospheric distillation column residue is processed in vacuum distillation column and again vacuum residue is formed. And so, what we are getting crude oil, then atmospheric residue and then we are getting vacuum residue. So, if we go from crude oil to different residue, then we see the quality is degraded. So, viscosity increases, sulfur increases, nitrogen increases, asphaltenes increases, H by C ratio decreases and AP degree AP decreases, CCR increases. So, this clearly indicates that the quality of VR is much poor than the crude oil and the refinery is not that much interested with this VR to properly manage it, because this is of low value or negative value product for them. So, we need to convert this VR so that it will be managed properly and environmental pollution will be reduced. On the other way, the refinery can also add some value addition to the whole process. So, from this table it is clear to us that this residue is having higher viscosity, high sulfur, high average boiling point and H by C ratio is low and CCR is high. So, if we want to upgrade it, obviously the scope is there, we have to improve the hydrogen by C ratio. So, H by C ratio we need to improve. So, for doing this there are number attempts people try to do it, and like say solvent deasphalting and then thermal processes, hydro treatment etc. So, now we will see the how the solvent deasphalting and other process will help to improve it. And to understand that, we have to understand the residue, what the residual oil is. So, residue oil, it is high viscous oil in which we have asphaltenes and resins as well as some oil part. So, oil part is called say maltins as shown here. So, this is a maltin part, this is emulsion. In this emulsion we are getting is asphaltene and resins in the dispersed phase, and in the continuous phase we are getting the maltins. Now, if we can remove these asphaltenes and resins from this whole system, then we can get the maltins which is desirable and we can recover that oil for our applications. So, how we can do it? Obviously, because the presence of these asphaltenes and these resins and other where also metals are also there. So, it gives a higher viscosity and higher salt content, higher heavy metal content, higher sulfur and nitrogen content and higher naphthenic acid content. So, this content, this is the properties of this. Now, we need to remove these things, the asphaltenes from this. So, how it can be done? We can use some solvent. So, that solvent will take these meltings from this whole emulsions and it will be broken and some meltings can come to the solvent. So, that is one way of solvent deasphalting. Otherwise, you can apply thermal heat here. So, heat will break or crack the molten molecules, and after certain extent of cracking, this emulsion may break, and then that broken emulsion, under that conditions the asphaltenes can be separated from the oil. And hydroprocessing can also take place to hydrogen addition. So, these moltens will be converted and then this will be separated. So, these three major routes which can be applied for the removal of these asphaltenes from the melting and to get pure quality oil from the residual part. So, on the basis of this, the methods which are developed, one is solvent deasphalting, another is thermal conversion based process, that is cracking and gasification, and hydroprocessing based process, hydrocracking. Now, thermal and hydrocracking may be catalytic or non catalytic type, and some thermal cracking routes are visbreaking, delayed coking, fluid coking, plexi coking, hydro visbreaking, donor solvent cracking and hydropyrolysis. So, these are the different routes people have applied for the upgradations of the residue. So, the total upgradation technologies we can classify into three major category. One is hydrogen addition method, another is carbon rejection method, and another is other method. So, in hydrogen addition method we add hydrogen. So, hydro desulfurization and hydrocracking, these are two, and different types of reactors have been used, that is fixed bed, ebullated bed and slurry bed reactor. Now, carbon rejection methods, one is thermal cracking, catalytic cracking and solvent extractions we can apply. So, these thermal cracking, visbreaking and delayed coking and coker it is mentioned here, and catalytic cracking, FCC, RFCC, residual fuel catalytic cracking. FCC is fluid catalytic cracking, RFCC is residual fuel catalytic cracking, and solvent extraction also, that is rejects carbon. So, carbon rich molecules are settled in the extractor, so and get separated later on. So, then other technique is your gasification. So, these are different techniques. Now, first we will discuss this one, solvent deasphalting process. Before that, we see around the world what type of techniques are used, and if we see this figure, coking is mostly used, that is 40.29%, then visbreaking or cracking say 33.89%, then you see here hydrotreating and then hydrocracking and then deasphalting is 3.62%. So, these are different technologies which have been applied around the world to upgrade the residual part. So, now we will be conducting this one. Before that, we will see how we can select this technology, which one will be selected for what type of feedstocks. This slide shows us with reference to some properties of 340 degree centigrade residues. So, various crudes if we take, and then we can measure the nickel and vanadium and we can measure the CCR. So, carbon residue, CCR, carbon residue, condensation carbon residue and nickel and vanadium concentration, both amount can guide us what process will be more suitable. So, if more metal is there, then more carbon is also there, we can go for carbon rejection. So, these are carbon rejection zone, metal is also more and carbon is also more, but if we have carbon is less, metal is also less, we can go for fluid catalytic cracking, and hydroprocessing range are the in between one, more preferable. So, this way we can select a particular route which will be more suitable for a particular feedstock. Now, we are coming to solvent deasphalting. So, the term itself says the solvent de-asphalting. So, we will be adding some solvent. So, maltines will come into the solvent and asphaltines will be separated from the feedstock. So, that is the main objective. So, vacuum residue we are using in the SDA process. So, asphaltine will be separated at the bottoms we are getting asphaltines or it is pitch we are getting, and then solvent plus oil. So, that is called de-asphalted oil. So, after de-asphalting the oil which we are getting, that is de-asphalted oil plus solvent is coming here. So, that can be used for different FCC for further purification or improvement of quality. FCC, hydrocracker, thermal cracker as a lubes, we can use it as a lube based stock. And pitch or asphaltines part which we are getting, that can be used for bitumen road making, or that can be used in circulatory fluidized bed combustor for power production or steam generation, and that can also be gasified, and that syngas can be used for power applications for steam or production, hydrogen production, petrochemicals or as a fuel itself. So, these are the overall concept of solvent de-asphalting process. Now, we will see this flow sheet which explains the SDA process. So, here we are getting feed, then feed has to be mixed with some solvent. So, solvent we are getting initially we add, then we get the recovered solvent. So, solvent plus feed we are mixing here. So, it is going to extractor. So, extractor on certain conditions, temperature, pressure is maintained and RPM etc., proper mixing is provided. Then we get 2 phase, it is allowed to settle, we get 2 phase. One phase we are getting asphaltine phase. So, it is going there and then heat recovery takes place and then it is coming to pitch stripper. So, we get pitch here. So, again some flushing tap arrangement. So, it is coming here and then flushing we are getting some liquid part, if solvent comes here. So, that can also goes off and it is coming here and then it is going to mixer and condenser. After condenser this solvent is recycled and here we are getting the pitch which we are having, and from the extractor the upper de-asphalted oil along with the solvent it is going and it heat exchange is taking place here. Then it is going to boiler and then DAO separator. So, DAO de-asphalted oil and solvent we have to separate it. Now, solvent has boiling point and de-asphalted oil components also have boiling point. So, those are not similar. So, if we apply heat and then the solvent will be in vapor phase, that we can go there and it can mix here and can be added here extractor, and then de-asphalted oil along with some solvent it comes, then it will be coming to here. So, de-asphalted oil will be separated in the stripper section and then solvent will also be come through these routes and then it will be recycled. So, solvent is recycled from the bottom is also recycled and recovered and recycled, and from the DAO separator also solvent is recycled and is recovered and recycled. So, that way solvent is recovered and recycled. That recovery of solvent is very important. Now, people have used 2 routes for its recovery. One is use of evaporators sequentials and then another is the operation separation of solvents at supercritical conditions of the solvent. So, DAO plus solvent, this mixture is heated to supercritical conditions of the solvent and then solvent is recovered from it, and in that process the efficiency is more. So, now we will be making some discussion on that line. Before that we will see the properties of the solvent and de-asphalting solvents. So, what can be the good solvent? Obviously, the liquid hydrocarbons, low molecular weight hydrocarbons like say propane, it may be butane, it may be pentane. So, normally it may be hexane also, but normally these propane, butane and pentanes have been reported in literature and have been used for the separation. So, once we use the low molecular weight hydrocarbon, then the molten part which will come to this, because the density is less here, all the asphaltines will be removed, and lighter solvent propane and isobutane that are higher selectivity these are having and reject all resins and asphaltines and suitable for production of lube oils. And heavier solvents if we use, that is pentane and N-butane, then and light naphtha can also be used. In that case, less selective than lighter solvents and then produce higher yields of DAO and DMO. So, deasphalted oil production is higher. So, produce higher yields of DAO. So, if we use more butane and pentane, it will be able to take more maltings, because its condition changes, it operates at higher temperature. So, higher temperature means more maltings can come here. So, now we will see the general properties of the solvents. So, solubility of oil decreases with increase in temperature, then more selective at higher temperatures exhibit lower critical solution temperature. So, lower the critical temperature, that recovery part will be easy. So, now process variables for this process. So, what is the, we are interested to get the oil part from the residue. So, solvent, how much solvent we are using, that will play a role, solvent to feedstock ratio and the solvent composition, solvent to feedstock ratio. So, selectivity improves by increasing solvent to feedstock ratio at constant DAO yield, and economically we have to optimize it. Obviously, more solvent, more purity of the product we will get, and but we have to optimize about with the economy, and the solvent composition, blends of light hydrocarbon solvent can be used, and then it increased operating flexibility. If we use the blends, then flexibility will increase, and temperature also important, because this temperature gradient will help the transfer of the oil phase from the residue to our solvent. Oil solubility in solvent decreases with increase in temperature, and temperature gradient improves separation between DAO asphalt phases, and pressure also maintained above the vapor pressure of the solvent. Now, we will see the comparison of some solvent and the DAO and the deasphalting process. So, if we have some SR, we have feed, then we have propane, we have propane butane, or we have butane, we have pentane. So, different solvents we are using in the deasphalting process, then we will be getting DAO as well as we will be getting asphaltenes. Then we will see how the properties of DAO and asphaltenes are changing with the variation of these solvents. So, here yield, DAO yield is say 29%, and then we are, when it is propane is used, if we use propane butane 46.8, if we use butane again 67.3, if it is pentane then 82.8. So, with the increase in carbon number, we are getting more DAO, but the same time we will be getting lower quality. So, higher solvent recovery is possible here, higher oil recovery is possible by this way, and then but the quality you see, the API gravity is decreased, here 21, here 16, here 12.1, here 10.3. So, we are getting more oil, but we are compensating, we are compromising with the quality with using higher carbon number in the solvent. So, viscosity also similar way increases, that means more oil is coming to the solvent, and then CCR is also increased, and the oil part which is coming to the solvent are having higher carbon than it. So, that is why CCR is also increased in this case, and sulfur content also increased, because the bottom which is going to the VR, that is coming to the DAO part, that is why sulfur is also increasing. The metal contents is also increased with the increase of the carbon number in the solvent. And if we see the asphaltene, then also softening point, if we see softening point increases, and then penetration point decreases, it is not that soft. So, penetration is not possible in this case, and specific gravity also increases. Why it is? Because more denser particles or molecules are coming to the DAO part with the use of heavier hydrocarbon or hydrocarbon with more carbon number. So, this is the comparison of different types of solvents when it is used for deasphalting purpose, and now we will compare about the operating conditions. If we use propane, butane and pentane, then the extraction temperature is different. For propane it is 50 to 80, for butane it is 100 to 130 and pentane is 170 to 210. So, that is one reason why we are getting more heavier part in the solvent and the DAO part. And then pressure range, we are getting 3.5 to 4 megapascal in case of propane, butane it is say 4 and pentane it is 4, and solvent ratio is high here. So, butane solvent ratio lesser, pentane is further lesser. So, higher the solvent than the feedstock, higher solvent to feedstock ratio, we will be getting more pure quality product or better quality product. So, that propane when we use, then we can use the feedstock for lube oil base stock production. Then we are coming to solvent recovery. So, evaporative mode and supercritical mode already we have discussed. So, in case of evaporative mode we can use multiple effect evaporator up to 3 stages and series of progressively lower pressure flashes followed by stripping. Just in the flow sheet also we have seen some stripping is there, flashing was there and then stripping was there. So, supercritical mode if it is used, then it becomes more energy efficient, say phase separation at above critical temperature of solvent, above critical temperature of or at the critical temperature of solvent is possible, and 85 to 90% solvent recovered as lighter phase for heat exchange and recycle in the process, and recovered solvent has very low DAO content, that the purity of the recovered solvent is higher if we use the supercritical mode of operation, and then remaining solvent from DAO recovered by flushing and stripping. So, solvent recovery is higher, quality is higher, but we have to optimize with the cost also, economic factor also. Now, we see the comparison of different process. So, if supercritical unit, triple effect evaporator, double effect and single effect. If we use single effect, that is 280 unit say energy cost, and it is double it is 170, triple effect 150 and for supercritical 100. So, if we use supercritical unit, the relative energy cost is less, and it also more energy efficient approach and utilities saving up to 40% with heavier solvents, more compact unit this one, and savings in capital investment for gross root plants is 15 to 25%. So, this is the advantage of applying supercritical condition. Now, we will discuss on deasphalting tower or the extractor which we had, in this case extractor. So, here we can get some internals. So, column internals may be baffle trays, it may contain rotating disc contactor, it may have packing or it may have parallel interceptor plate. So, these different types of options are available. So, baffle plates, baffles are mostly used in PDA plants in India, and that RDC and PIP, the UOP and Foster Wheeler, they offer the choice for the PIP or RDC. And structure packing is used for ROSE units, that is called residual oil supercritical extraction unit, ROSE unit. So, currently used in all ROSE unit the packing, and advantage of this is that better quality of DAO and higher circulating solvent purity, higher capacity for existing solvent deasphalting units and lower operating cost. And PIP assembly if it is used, that I have mentioned that UOP and Foster Wheeler has given their options which PIP or rotating disc contactor, but it has some advantage, the PIP has some advantage, that increased separation efficiency and reduced size of extraction vessel and reductions in the capital and operating costs. So, these are the comparison of different deasphalting design, column design. Now, we will see the processing of DAO and asphalt. So, what we can do with the DAO and asphalt? So, once we can get DAO, we can get lube oil, and lube production increased by approximately 20%, and that due to the use of this deasphalted oil, and cracking 1/3 of catalytic cracking feed in a refinery can be of DAO, and hydrocracking economical, consumes less hydrogen, less investment. So, we see that if we can produce DAO, so that can improve the economic of the plant also, because it will give more products which are valuable in market. Then asphalts can be used as a blending, it can be used as a bitumen or fuel oil or road making, and it can be going to visbreaking, so that minimizes the need of cutter stock, and then it can be gasified also. Here we will see some technology licenses. So, if we Kellogg, Brown and Root, they are giving the technology ROSE, the residuum oil supercritical extraction, and more than 33 supercritical units are used in commercial scale with this capacity. And UOP Foster-Wheeler solvent deasphalting process, they are also 50 units, and IFP France, there are also 7 unit, and then IIP Dehradun and EIL India, they have 2 conventional plants, and RIPP China, they have 5. So, these are some basis of 2002 data, also it is very old data, but ExxonMobil also offers PDA technology. So, in India we are having the conventional PDA technology, and we will see the what that PDA is, propane deasphalting, and propane deasphalting we use the propane as a solvent for the removal of asphaltins from the vacuum residue, or any heavy lube oil base stock can be produced from this process, and cylinder oil can also be produced, and the operating condition is 50 to 80 degree centigrade and 6 to 20 solvent to feed ratio, and pressure more than the vapor pressure of the propane. So, these are the conditions, and we see the HPCL Haldia, IOCL Haldia, CPCL and HPCL, they are producing DAO with this quality, the kinematic viscosity and CCR. So, these values are provided here. So, obviously, you see the viscosity is reduced and the CCR is also reduced. So, by this process, and good amount of DAO is recovered from the vacuum residue, which are cleaner in nature. Now, we see the propane deasphalting status. So, HPCL Mumbai, CPCL Chennai, IOCL Haldia. So, their capacity is 5,48,000 MMT per annum, and for this CPCL it is 5,74,000 MMT per annum, and it is for 6,50,000 MMT per annum, and these are the technology licensor IIPIL, and this is in case Romanian expansion by EIL ROSE. So, these are the some deasphalting technology which is implemented in the country. So, all plants produce lube oil base stock, and solvent recovery, evaporation mode or supercritical. The supercritical mode IIP and EIL have developed the know-how on this process. So far we have discussed on the solvent deasphalting part, and the next class we will discuss the other part of the vacuum residue upgradation. So, thank you very much for your patience.